We were discussing laminar flow in a pipe, okay, in the last few lectures. We had carried out a momentum balance in order to derive the conservation equation, and then from that, for a steady flow we had determined what was the relation between the pressure difference and the velocity in the pipe, and from that the correlation between the friction factor and the Reynolds number. And in the last lecture we had solved a problem for determining the change in height between two tanks due to the flow in the pipe. So, the conservation equation rho partial Vx by partial T minus partial P by partial x. Okay. If you use the Newton's law for viscosity, okay, you get rho partial Vx by partial T is equal to incompressible flow, density is a constant. I can write this equivalently as partial Vx by partial T is equal to okay. And if in addition the momentum diffusivity is a constant, the equation becomes partial is equal to nu by r and if in addition it is steady, then the variation of velocity with respect to time is 0. Okay, the variation of velocity with respect to time is 0 if in addition it is a steady flow. Okay. So, all of this calculation was done without any body forces. Okay. All of this calculation was done without any body forces. Okay. What if there is a body force in the x direction? Okay. If the pipe is horizontal, of course, there is no gravitational force in the x direction, there is a gravitational force only in the radial direction. However, if the pipe is at an angle or vertical, there is a body force in the x direction. Okay. And in that case, you would have to add here an additional term rho gx, okay, the component of the body force in the x direction. Okay. And rho gx is a constant. I also told you that the pressure difference, if you apply a particular pressure difference across the ends of the pipe, okay, if rho gx, the body force, is a constant, and if you apply a pressure difference across the ends of the pipe, then the pressure is a linear function of x, okay, and the body force is a constant. Okay. So, you can easily verify by just taking the derivative of this with respect to x. Even if there is a body force density, d square p by dx square is still equal to 0. Okay. So, if I take d by dx of this, okay, if the body force density is a constant, this does still imply that d square p by dx square is equal to 0 and dp by dx is a constant. Okay. It still implies that d square p by dx square is equal to 0 and dp by dx is a constant. What that means is that I can define, okay, a dynamical pressure field, okay, which incorporates the effects of this. Okay. So, if I define P prime is equal to P plus rho gx x, okay. If I define P prime is equal to P plus rho gx x, that is, you are including the hydrostatic head in the definition of the pressure. This implies that partial p prime by partial x is equal to partial p by partial x plus sorry. Therefore, these two terms together I can just write it as minus partial p prime by partial x. Okay. Okay. So, the effect of a body force can be obtained by just redefining the pressure, okay, from p to p prime. Okay. So, then my equations all become in terms of p prime here. Okay. So, in that sense this formulation is general. Even if there is a body force density, that body force density can be incorporated into the definition of the pressure, and then this corrected pressure, okay, the equation in terms of this corrected pressure p prime is still exactly the same as what we would have had if there were no body force density. Okay. So, this formulation is general. Okay. So, any body force density in the x direction can be incorporated into the definition of the pressure. Basically, a pressure gradient and a body force density are one and the same, okay, for an incompressible flow. Okay. The pressure gradient and the body force density serve exactly the same role in the momentum conservation equation. Okay. So, that was one. Okay. So, that is one approximation that we had made originally, where we had neglected the body force density, but I just showed you that even if there is a body force density, I can just incorporate it to the definition of the pressure, and then nothing further changes, okay, because rather than having a difference in pressure between the two ends, I have a difference in the pressure plus the body force density between the two ends. Okay. The second approximation we have made here is that the linear relationship between the stress and the strain rate, okay, and the velocity gradient. Okay. And the third approximation we made was for neglecting the time derivative, okay, of the pressure. So, now I will try to derive the try to see the more general case where the relation between the stress and the velocity gradient is not a linear relationship. Okay. You recall that I told you that for a power law fluid, tau x z is equal to k into partial V x by partial tau x r, my apologies. Into where k is the flow consistency index and the n is the power law index. Okay. So, in that case, how does the velocity profile change, and how do we determine the velocity profile and thereby the friction factor, okay, correlation. Okay. Okay. So, even if the fluid is a power law fluid, okay, the momentum conservation equation at steady state is just still equal to 1 by r partial by partial r of r tau x r minus partial p by partial x. Okay. dP dx is still a constant, because if I take the derivative of this entire equation with respect to x, the shear stress is independent of x because the velocity is independent of x. We saw from the incompressibility condition that the velocity has to be independent of x. Therefore, the shear stress is still independent of x. So, if I take one derivative, I will get, okay, in this particular case it is a total derivative because it is steady, d square p by dx square is still equal to 0. Okay. Okay, d square p by dx square is still equal to 0 even in this case. Okay. Therefore, dp by dx is still a constant, okay, which means that partial by partial r of r tau x r is equal to r dp by dx. R tau x r is equal to r square by 2 dp by dx plus some constant a, okay, and tau x r is equal to r by 2 dp by dx plus a by r. Okay. The constant a can be determined from the condition that at r is equal to 0, okay, at r is equal to 0, tau x r is finite. Okay. The shear stress cannot increase indefinitely as r goes to 0. Okay. Therefore, that implies that if a is non-zero, then the shear stress goes to plus or minus infinity at the center of the tube at r is equal to 0, which is not physical. Therefore, the boundary condition implies that this a has to be equal to 0. Okay. Therefore, I can write tau x r is equal to r by 2 dp by dx. Okay. And it is more convenient to write this as minus r by into minus dp by dx, because I told you that when dp by dx is negative, the velocity is positive. Okay. So, minus dp by dx is a positive quantity. Okay. And the wall shear stress is the value at, okay, r by 2 dp by dx at r is equal to capital R. That is the wall shear stress, which we will need later for the friction factor correlation, okay, which we will need later for the friction factor correlation. So, now the velocity can be determined from the constitutive relation, okay, k into dvx by dr into dvx by dr whole power n is equal to minus r into and you can integrate this. Okay. So, you will get dvx by dr, okay, so should be n minus 1, okay, is equal to minus 1 by 2 k dp by dx power 1 by n, okay, into minus r power 1 by n. In this particular case, since r is negative on the right side, dvx by dr has to be negative, that is vx has to decrease as r increases. Okay. Therefore, vx will be equal to minus 1 by 2 k dp by dx whole power 1 by n. Note that minus 1 by 2 k dp dx is a positive number, okay, because dp by dx is positive, okay, into minus r power n plus 1 by n by 1 plus 1 by n. Okay. Note that integral dr times r power a is equal to r power a plus 1 by a plus 1. Okay. So, if a is 1 over n, integral dr r power 1 by n is equal to r power 1 by n plus 1 by 1 by n plus 1. Okay, so that is what I have here, okay, plus a constant of integration a. The constant of integration, I should note it as b. I have already used a one time. So, this is b at r is equal to capital R, V x is equal to 0. Okay, that condition can be used to determine what is the constant. Okay. And you will get an equation for V x is equal to minus 1 by 2 k dp by dx whole power 1 by n into doing the integration. Okay. 1 by n plus 1 is n plus 1 by n. So, this first term can be written equivalently as n by n plus 1. So, this is we have got V x as a function of r. Okay. Maximum velocity V max is equal to minus 1 by 2 k dp by dx whole power 1 by n into n by n plus 1 into r power n plus 1 by n. Okay, so, that is the maximum velocity. What is the average velocity? Is equal to 1 by pi r square cross sectional area times the flow rate, okay, 0 to r. Recall we had done this calculation for the flow rate before. Okay. Recall that we had done the calculation for this flow rate before, okay, for a pipe. Okay. We had taken a cylindrical volume of thickness delta r. Okay. So, we took a cylindrical volume of thickness delta r. Okay, and calculated the flow rate perpendicular to this. The flow rate is the velocity times the area of that annular strip, okay, times the area of this annular strip, which is V x times 2 pi r times delta r. 2 pi r is the perimeter, delta r is the thickness. Okay. So, the perimeter times the thickness is the area of that cylindrical strip, multiply that by V x and you get the area. So, this is 2 pi r dr into V x. And this 2 pi can be taken outside. So, I will just get 1 by 2 r 2 by r square integral 0 to r, okay, r dr times V x. And this velocity V x, I can take this entire prefactor out of the integral sign. I can take the entire prefactor out of the integral sign, okay, because it is a constant independent of r. Okay. So, I will get 2 by r square into minus 1 by 2 k dp by dx whole power 1 by n by n plus 1. Integral 0 to r dr into r power n plus 1 by n minus r power n plus 1 by n. And when I do this integral, you will get 2 by r square into minus 1 by 2k into r power n plus 1 r square by 2 minus. Okay. Okay. I have the second term is r into r power n plus 1 by n dr. Okay. Which is equal to r power 2n plus 1 by n dr. Okay. Integral of this. Okay. Between 0 and capital R. Okay. So, this is going to be equal to n by 3n plus 1 into r power 3n plus 1 by n between 0 and r. Okay. It's equal to n by 3n plus 1 r power 3n plus 1 by n. So, that is the expression. Okay. 0 and capital R. Then I have r power 3n plus 1 by n. Okay. Common factor. The first one is 1 by 2 minus n by 3n plus 1. And this term here, okay, this term here is basically 3n plus 1 by 2 minus 2n. Okay. Okay, so, it is equal to n by 2 into 3n plus 1. Okay, so, I missed out a factor of 1 by n here, kindly note that. That is this one. So, the final expression I will get for the average velocity is VAV is equal to 2 by r square okay, into n by 2 into 3n plus 1. And these will cancel out, the factor of 2 here, and r square will cancel out with r power 3n plus 1, and finally I will get minus 1 by 2k dp by dx whole power 1 by n into r power n plus 1 by n, okay, into n by 3n plus 1. So, this is the expression for the average velocity. You can verify by setting n equal to 1 that you get the exact same relationship for a Newtonian fluid. Okay. Now, we have to relate the friction factor to the Reynolds number. Okay. Recall that the friction factor is equal to tau w by rho v average square by 2 for this case. Okay. Tau w by rho v average square by 2. Okay. And this has to be related to the Reynolds number. Okay. So, we have to define the Reynolds number for this case. The Reynolds number is equal to rho v average power 2 minus n into d power n by k. Okay. This we had derived earlier when we using dimensional analysis for the Reynolds number for a power law fluid. Okay. Note that the shear stress tau xr is equal to k into dvx by dr into dvx by dr power n minus 1. Okay, that was the power law relationship. Okay. The left side has dimensions of m L inverse t power minus 2. Shear stress is force per unit area. Okay. It's equal to dimension of k into t power minus n. Okay. Because dvx, so dvx by dr has dimensions of, okay, the dimension of dvx by dr is equal to L T inverse by L, which is basically equal to T inverse. Okay. So, dvx by dr power n will have T power minus n. Okay. Therefore, K has dimensions of m L inverse T power n minus 2. Okay. If n is equal to 1, it is a Newtonian fluid, it is L inverse T inverse. Okay. So, therefore, I can just from dimensional analysis, this one numerator is m L power minus 3, okay, L power 2 minus n T power n minus 2, okay, and L power n divided by m L inverse T power n minus 2, okay, and this is equal to dimensionless. Okay. So, this is the definition of the Reynolds number that we had used previously. Okay. And the friction factor is equal to tau w by rho v average square by 2. Okay. In the limit of, for a laminar flow, I would expect this to be go as inverse of the Reynolds number. Okay. So, I can rewrite this as k by rho v average power 2 minus n, okay, d power n, okay, into tau w by k v average power n d power minus n by 2. Okay. I have just done a rewrite here. Okay. If you multiply these two terms in the denominator, okay, so yeah, okay, if you just multiply these two terms, okay, this k will cancel out, okay, this k will cancel out, okay, and v power n into v power 2 minus n will give me v square, and d power n and d power minus n will cancel out. Okay. So, this is exact same expression, except that I have now expressed this as 1 over Reynolds number into tau w by k v average power n d power minus n by 2. Okay. And I have the expression for the wall shear stress. Okay. I had the expression for the wall shear stress earlier. Okay. tau w is equal to r by 2 dp by dx, okay, which was this expression. Okay. And I have V average power n, okay, is equal to, okay. I have to take this expression for to the nth power, okay, this expression for V average to the nth power, okay. And n by 3n plus 1, okay, power n. That is V average power n, okay. Tau w is negative because dp by dx is negative. So, I have to take the magnitude here, okay, the magnitude of the wall shear stress, because the wall shear stress is acting in the negative x direction. Okay. Therefore, the friction factor is equal to 1 over R e, okay, into r by 2 dp by dx, okay, divided by V power n, V average power n, which is minus 1 by 2 k dp by dx, into k. So, let me be careful here. In the denominator, I have k into 1 minus 1 by 2 k dp by dx, okay, into r power n plus 1, okay, into n by 3n plus 1 power n, okay, into the diameter is r by 2, okay, power minus n by 2. Okay. And you can easily verify that the factors of k will cancel out, the factor of dp by dx will cancel out, okay, and all factors of r will also cancel out. I have r power minus n here, n plus 1 here, and r here. Okay. So, all of those will cancel out. Okay. And I will finally get this is equal to 2 by R e, okay, into 2 into 3n plus 1 by n power n. So, this is the friction factor expression for the flow of a power law fluid in a pipe, evaluated the exact same way. We got the wall shear stress, velocity profile, average velocity, definition of Reynolds number, and then calculated the friction factor. In this case, for a pressure driven flow, the shear stress is exactly the same, because the expression for the shear stress is the same as that for a Newtonian fluid. Okay. This expression for the shear stress is the same as that for a Newtonian fluid. The shear stress is related to the velocity by the power law expression, which is different. Okay. And you can solve that in order to get the velocity profile, the shear stress, and the correlation for the friction factor. Okay. So, this is for a case where you do not have a linear relationship between the stress and the strain rate. Okay. And all of this so far has been for a laminar flow. In the next lecture, we will start discussing the friction factor versus Reynolds number for a turbulent flow. I will first discuss the mechanism of transition to turbulence, the features of turbulence, and then the structure of turbulence. I will continue this in the next lecture. I will see you then.